Okay. Okay. So as I said, we're starting our next module, magnetic, and well, this new module is about magnetic properties. So what we're gonna cover today, hopefully, is gonna be basic concepts in magnetism. So this is just to like remember some basic equations regarding magnetism. Then we'll see the five main types of magnetism: dia, para, ferro, antiferro, and ferrimagnetism. And then we'll just briefly sort of introduce some theories that kind of explain the different phenomena in magnetism. Okay, so let's begin. Let me use, okay, there we go. So let's imagine you have a magnetic material suspended from one of the arms of a sensitive balance, and then after some time you allow it to reach into an inhomogeneous magnetic field. Well, that material will have different responses depending on the type of magnetic material it is. For example, if you have a diamagnetic material, well, that material will be expelled from that field. But if you have a paramagnetic, a ferro, or an antiferro, or a ferrimagnetic material, the material will be attracted to that magnetic field in different degrees, obviously. So if you consider that you're basically attracting the material, there will be a force that causes that attraction, right? Or that causes that that repulsion in the case of a diamagnetic material. There's obviously a force, right? So, well, that force exerted by the magnetic field can be represented by this equation. And you might be wondering, well, what's the meaning of this equation? So obviously this is the force. B becomes the volume of the material or the volume of the sample. And mu naught is the universal constant. We'll see this constant all throughout this module. This constant is, as I said, the universal constant. That's basic, or also called the permeability of free space. It's again a constant. The value is 1.257 times 10 to the minus 6. Let me just write that if not, so mu naught equals 1.257 times 10 to the negative 6. Okay. What's chi? Chi is also a constant that you guys should start familiarizing with. It's called the susceptibility. The susceptibility basically expresses how responsive a material will be to an applied magnetic field. So basically, literally, how susceptible to a magnetic field a material is. That's why it's called the susceptibility. Okay. And this term that you see here, dH, or the derivative of H with respect to X, is just the change in the magnetic field strength. As you may imagine, H is the magnetic field or magnetic field strength. So dH dx is the change of the magnetic field strength in the x direction, right? I think that's obvious. This is one of the most basic, simple equations that allow me to get or to calculate the force that a material or that is exerted on a material due to a magnetic field. And here you can see the constants. You can see chi. Okay, chi is unitless. We'll always use the SI units, right? It's unitless. And you can also see mu. Mu, by the way, is the same as mu is just the mu is just the permeability of a material, but not in free space, right? So mu naught, the one we have here, let me click on this. So mu naught is the permeability of free space, right? So that's one single constant, but then we have mu, that's just the permeability, but in general. So we have different constants. You can see it's also unitless. And then that, if you see the combination of these two constants, chi and mu, will determine the type of magnetism the material has. And you can see here for different metals, you can see the values there. Okay. So let's keep looking at more equations. This is again the field strength, or the magnetic field strength will be proportional to the current that has been generated. The number n is just the number of windings or the number of turns. So basically, if you imagine usually how or how magnetism was discovered, actually, you have a tube, right? And then basically you put that tube through a series of coils. Let me use other color. So you put, oh no, I'm terrible at drawing, but let me, so imagine these are all coils, right? So it's just basically coil, or a coil that has a lot of different turns. So that coil is the one that is exerting or creating the magnetic field on my tube, on my sample, right? So that's what n is. N is just the number of these, turns, the number of these windings that the coil has. And the magnetic field strength is obviously inversely proportional to the length of that tube, right? Or that will be the same as the length of the whole coil, right? Of the solenoid, as it's called. Well, what else can we find? Well, if you want to even enhance that magnetic field, you can do it inserting, for example, iron into a solenoid, right? There's a parameter that can describe that enhancement, and that's actually the permeability, as I said. So this is the permeability, normal permeability. Remember, this is permeability of free space. Okay. Well, that magnetic field strength that that we create within a material is called the magnetic induction or magnetic flux density, and that is B. Okay, So B is just the magnetic induction, or it's actually more well known as the magnetic flux density, okay, or magnetic flux sometimes. The magnetic flux is given in Teslas, okay. The units of the magnetic flux is a Tesla. And you can see there's a relationship then between permeability, magnetic field strength, well, this is just again a constant, and that relates to the magnetic flux density. So the relationship between permeability and magnetic field strength gives the magnetic flux. And then there's also a relationship, as you can see, between susceptibility and permeability, right? So remember this is susceptibility, and remember this is permeability. So there is this relationship between susceptibility and permeability, okay? So permeability equals 1 plus susceptibility. Now, if we look at this equation, actually, we have different cases. So when we are in empty space, and like in general, for most practical purposes, even for air, susceptibility equals 0, and therefore permeability equals 1. Now, what happens if I have diamagnetic materials? When I have diamagnetic materials, usually chi is very small and negative. What does that mean? That mu equals, or the permeability is less than 1. And you can see the table here. For diamagnets, you can see the values, right? For chi, it's quite small. You see the values for chi, very, very small. But you see, as we said, mu is less than 1, because they're also negative. You see here the values, right? That's for diamagnets, okay? Now, what happens for para and antiferromagnetic materials? Well, chi is small, but is positive. Therefore, mu is going to be greater than 1. And you can go back to your table and see for paramagnetic, it's positive, yes, small but positive, so mu greater than 1. You can see that. Now, what happened for ferro and in ferromagnetic materials? Chi and mu are both large and positive for these materials, and you can see, I think in the table we have ferromagnetic. Oh, sorry, no, we don't. So then don't. Oh, we have ferro. Yeah. So you can see chi is large. You can see mu is also large. You can see the difference between these values and even all of this here, right? So for ferro and for ferromagnetic materials, chi is very large and positive. Mu, chi is big, then mu will also be big, right? Because obviously in those terms, even the 1 probably even doesn't affect the value, right? So I'm just adding 1 to a value of times 10 to the cube times 10 to the 4, 10 to the 6. Okay. Any questions, guys? Is it clear so far? So even though we'll see this later, I already want to mention that all of these magnetic constants, so permeability, susceptibility, they're all temperature dependent, except for diamagnetic materials. And even if you consider ferromagnetic materials. The susceptibility for ferromagnetic depends on the field strength. Okay? So basically, ferromagnetic materials or the constants are not only affected by temperature, but also depend on the field strength. Okay. Let's keep looking at more basic concepts in magnetism. So if we are in free, empty space, we know that the magnetic flux and mu naught times h are identical. Why is that? Because if we are in free space, this just becomes 1. So I only have this and that. So yes, the magnetic flux equals mu naught, or the permeability of free space, times the magnetic field strength. Okay? Now, inside the magnetic material, the induction has that free space component that, as I said, is this, right? But it also has a contribution to the magnetic field due to the presence of matter, because there's matter inside that magnetic material. And so that can be represented by mu naught again times m. Now you might be wondering what m means. Well, m is the magnetization of the material. Okay. So if you look at this, actually, the magnetic field strength, the magnetization of the material, and the magnetic flux, they're all vectors. Okay? We're just gonna use their modules, but they're all vectors. Now, let's combine this equation, this one, and we get this. M, the magnetization, equals chi times h, so the magnetization is directly proportional to the field strength and the susceptibility. Okay. And these are equations. There's a lot of work to derive them. We're not going to do that. Just explaining some basic equations that we'll need to build from here onwards the quantum concepts of magnetism. Okay. So B was actually the magnetic flux density, right? So that we could say this is actually the magnetic flux per unit area, right? That's the magnetic flux density. So if we actually want to get just the magnetic flux, the total magnetic flux, not per unit area, we just multiply times the area, right? The magnetic flux density, or the magnetic flux per unit area, times the area, I will get the magnetic flux, the whole value, right? So that's how you represent the magnetic flux. Now, let's see that in free space, the magnetization equals 0. So if magnetization equals 0, and you remember this equation, right? You can easily say, oh, okay, because remember you have an equation for M and for B, right? So the magnetization equals 0 in free space. We'll get that the magnetic flux for free space equals the permeability of free space times the magnetic field strength times the area. Now, let's define, or yeah, I guess this is the last concept we're going to define, at least for these basic terms. The magnetic moment. What's the magnetic moment? This is called the magnetic moment. Obviously, that will be a vector too. So the magnetic moment is just, or these equations just means that the magnetization is the magnetic moment per unit volume, right? That's all what the magnetization is. The magnetization is just the magnetic moment per unit volume. Okay, so these are all the basic equations that we'll need. Just the relationship. I'm sure you've seen probably a few of them before. And maybe most of these terms might be new to you. So it'd be nice for you to start familiarizing with these terms. Magnetic flux per unit area, magnetization, magnetic field strength, permeability, susceptibility, permeability of free space. So you just need to start familiarizing with these terms, okay? Now, let's actually get into more interesting stuff, not just equations. As I said, these are, equations that you don't need to memorize. Remember, I always give you a cheat sheet where you can find all the equations, but you do need to understand what they mean, and you need to understand what the terms are, right? So let's start getting into the different types of magnetism. And let's begin with diamagnetism, right? You might remember actually at least some brief idea of this concept from your ceramics course, because there we saw magnetic properties for ceramics, and you might remember these terms, right? The idea here is just to go a bit deeper and probably relate these the behaviors we saw back in ceramics to some theories and even take them to quantum level. Okay, so what is diamagnetism? Well, let's again imagine that you have an external magnetic field, and that external magnetic field will induce a change in the magnitude of all the inner atomic currents that you have. So basically, that magnetic field will accelerate or decelerate those orbiting electrons that the material has. And once it does that, the magnetic moments of those electrons will be in the opposite direction from the external magnetic field. So why is diamagnetism? It's that phenomenon where all of my electrons, or the spins of the electrons, are aligned in the opposite direction from the external magnetic field. And that is because that magnetic field is either accelerating or decelerating the orbiting electrons that my material has. Now, that would be just assuming that all materials have all electrons bound to the nuclei of the atom, right? But that's not true, because remember, for example, in metals, you also have free electrons. It's not that you only have bound electrons, you also have free electrons. Well, those electrons with that external magnetic field are induced to move in a circular path. And that leads to a second contribution for the diamagnetic moment. Right? So basically, for diamagnetism, we have two contributions. One is just the external field by itself is accelerating or decelerating the orbiting electrons, the bound electrons the material has, plus, especially in those materials like metals that have free electrons, the second contribution will come from those free electrons that, because of that external magnetic field, are induced to move in a circular path. And that obviously generates a magnetic moment, right? And that's what results in diamagnetism. And actually, for example, in metals, are those outermost electrons, those free electrons, the ones that contribute the most for the diamagnetic properties in those metals that have this property, right? Okay, now what happens with superconductors, for example? Well, superconducting materials are able to expel the magnetic flux when they're in the superconducting state. So that means that a superconductor behaves in an external magnetic field as if the magnetic flux density is zero inside the superconductor. So basically, the superconductor, when it is in the superconducting state, it's a barrier for magnetic flux lines. So that magnetic field, that external field, cannot penetrate the superconducting material if the material is in the superconducting state. Therefore, the magnetic field strength, and you can see that just from these equations, right? From this equation right here, the magnetic field strength will be equals, I mean, just opposite sign to the magnetization, and therefore the susceptibility equals -1. And that's why, for example, the susceptibility in superconductors is, as you can see there, is -1, compared to if the same material, if you put the same material in normal state, so not in the superconducting state, it will have a value of about 10 to the -6. So imagine when it's in the superconducting state, it has a change of in 6 orders of magnitude. The susceptibility has a change of 6 orders of magnitude. And it's actually that strong diamagnetism of these superconducting materials, the one that is used for frictionless bearings. And that's, for example, why a lot of companies now are looking or are researching a lot on how can I improve just the mechanical properties, because the magnetic properties are already there of these materials. How can I use them? Because these bearings, that's the idea, they want to use these bearings so there is no friction because of this high susceptibility or this perfection in diamagnetism of superconducting materials, that so they can develop frictionless bearings. And why will it help to create frictionless bearings? Well, they wouldn't fail eventually, because remember, bearings usually fail by fatigue, right? Because of that constant friction between the ball and the track. You have frictionless bearings because of this. They will be repelling, so the bearings will be still rotating around the path, around the track, but now there wouldn't be any friction between one ball and the other, and therefore it will last a lot longer. Another example of these diamagnets, well, levitation. If you put a magnet over a superconducting material, you'll see, and remember that I think I even showed you a picture or a GIF in ceramics. If you put a magnet over a superconducting material, you know it will levitate, right? And that's because of this perfection of diamagnetism in superconducting materials. Okay? Any questions so far?
No, it's pretty much clear.
Okay. Let's go to paramagnetism. So, paramagnetism is attributed to a magnetic moment that is generated as a result of electrons spinning around their own axis. So now it doesn't have to deal with the fact of electrons orbiting around my atom. That was the case for diamagnetism. For paramagnetism, now it's actually that magnetic moment that is created as a result of electrons spinning around their own axis. So it's like Earth. If you remember, Earth is able to rotate around the wrong axis, right? And then also Earth rotates around the sun. So remember, one lasts 24 hours, the other lasts 365 days. So it's the same here. So electron orbiting all around the atom, okay, that's related to diamagnetism. Electron rotating around its own axis, well, that's paramagnetism. So, or that magnetic moment that is generated due to that rotation generates or produces paramagnetism. Now, remember that because of the Pauli principle, and you know that from chemistry, no two electrons that have the same energy can have the same value and sign for the spin moment, right? Remember that each electron state can only be occupied by two electrons, but one must be with a positive spin and the other must be with a negative spin. And that's why you remember, if you have like that electron level, you'll have one electron going up and one electron going down, right? The spins are opposite. You cannot have this. Remember, that is prohibited because of the Pauli principle. Now, that's at the beginning, right? So basically, electrons orbiting around their own axis, it generates a magnetic moment. Now, let's imagine you put an external magnetic field to that material. Well, that magnetic field is going to try to turn the unfavorably oriented spin moments in the direction of the external field. So for example, let's say you have only one electron in one of the electron levels, right? And you have a magnetic field in the opposite direction, well, that magnetic field is going to try to shift that magnetic field and align it. Sorry, it's going to try to align that spin, that electron, or the spin of that electron, and it's going to try to align it with the same direction of the magnetic field. Well, that is paramagnetism. Spin paramagnetism is slightly temperature dependent, but it's very weak. In general, paramagnetism in general is a weak effect. It's observed in some metals, in some salts, also in the transition elements. Okay. Now, what happens with rare earth elements, or some, and obviously the salts and oxides of those elements? Well, they have an additional source of paramagnetism. So now they don't only have this contribution due to the magnetic moment generated as a result of the electron orbiting around their axis. Now, there is also a magnetic moment that stems from the orbiting electrons. So when I don't have any external magnetic field, the magnetic moments in those electrons, they all will be randomly oriented. And that's why they cancel each other, and that's what we have in paramagnetism, right? They usually cancel each other, and you might remember that from ceramics. In paramagnetism, all the moments cancel one another without the presence of an external magnetic field. If I put a magnetic field, well, the net magnetization is going to be zero without the field. Now, if I put one, all those randomly oriented moments will try to align with a magnetic field. They will try to be in the same direction, and obviously I will not have now a net magnetic moment of zero. Right? Let's say I actually want to apply an external magnetic field, but I don't want my fields to align. Well, I can just do agitation, for example, thermal agitation, or any agitation, and that will counteract the alignment. So that will avoid that all the spins try to align with this with the direction of the magnetic field. And that's why also electron orbit paramagnetism is temperature dependent. Okay. So this second effect that's generated by electrons actually turning or rotating or orbiting, and that contributes to paramagnetism is stronger, and its dependency in temperature is stronger than this. Than this first effect that is just depends on the electron orbiting around their own axis, right? Now, how can I represent that temperature dependency of the paramagnetic materials? Well, it's governed by the Curie law, and what Curie law says is that the susceptibility is inversely proportional to the absolute temperature and directly proportional to the Curie constant. So C is the Curie constant and T is the absolute temperature, okay? Or just temperature. So susceptibility equals Curie constant divided by temperature. Now, that just for rare earth elements in their salts and oxides, right? But in general, for like most materials, the susceptibility was just adapted by Weiss, and that's why it's called the Fourier-Weiss law. And the susceptibility becomes equal to the Fourier constant divided by the temperature, or the absolute temperature, minus theta. And what's theta? Well, theta is just another constant. It's a temperature constant. May have positive and negative values. It's not really, or it doesn't really have a specific name. So it's just a constant that was adapted, and obviously it's empirical, to sort of model the behavior of most materials, or the dependency on temperature of most paramagnetic materials. And in general, metals, only a few exceptions, but metals in general do not obey the Fourier-Weiss law. So this law actually doesn't apply to most metals. Only a few metals like nickel, for example, follow this law. Iron also follows this law. But then talking about at least other metals, usually they don't follow. Then carbonates, chloride, sulfates, yes, obviously they do follow the Fourier-Weiss law. But metals at least, very few. Only nickel and iron. They are the two only that follow completely the Fourier-Weiss law. And then there are also like sulfates or salts, but like of different materials, like cobalt, like chromium, like manganese, but they're sulfates, not the metal itself. The sulfates or the chlorides of those materials follow this Fourier-Weiss law. Okay, so let's actually compare between para and diamagnetism then. In paramagnetic materials, the magnetic moment of the electrons is pointing in the direction of the external field, and that's what I was saying, right? When I put an external magnetic field, the idea is that all those unfavorably oriented magnetic fields will align, or sorry, spins or moments will align with the direction of the external field. So in that case, you can say that the magnetic moment actually enhances the external field because it's aligning with the external field. Diamagnetism, on the other hand, counteracts that external field. That's why para and diamagnetism oppose each other. Because in diamagnetism, what the spins are doing is actually aligning on the opposite direction of the external field. So one is enhancing the external field, the other one is counteracting that external field. Now, remember that this second contribution of paramagnetism is talking about orbiting electrons, right? And we said that, well, but didn't we say also that orbiting electrons have to do with diamagnetism? Wasn't that the whole idea of diamagnetism, that electrons orbiting around the atom? Well, yes. So, solids that have the orbital and the spin paramagnetism, they're clearly paramagnetic. If they have both, the spin is, remember, just the electron orbiting around the wrong axis, and the orbital is the electron orbiting around the whole atom. Well, they're clearly paramagnetic because it's just the result of the sum of both paramagnetic components. And obviously the material will be more paramagnetic than diamagnetic. You can find that, for example, in rare earth metals that have an unfilled F electron level. Now, what happens in most other solids? That orbital paramagnetism is quenched. What does that mean? It's hindered. It doesn't really become predominant. So most other materials will not have a big effect of the or the electrons orbiting around the atom will not have a big effect on paramagnetism, so it won't induce paramagnetism. Yes, those materials will still have the spin paramagnetism, so yes, these materials will still have that contribution to paramagnetism of the electrons orbiting around their own axis, because yes, that happens in most materials. But that contribution of the electrons orbiting around the atom is quenched or hindered in my in most other materials. Now, if I have a net spin paramagnetic moment, well, that will depend whether or not the magnetic moments of the individual spins cancel each other. So if they cancel each other, then obviously I will not have a net spin paramagnetic moment. If they don't cancel each other, just then yes, there will be a small net spin paramagnetic moment. Now, so I'm saying this, and this might be confusing. So let's actually give examples to it. Let's say a material that has completely filled electron bands. Well, that material will have the same number of electrons with spins up and with electrons with spins down, because it's filled. So all the electron bands are full. Well, in those cases, I will not have a net magnetic moment. And that's why, for example, in those materials that have filled electron bands, you will not have a net spin paramagnetic or net spin paramagnetism. So you will not have paramagnetism. And therefore, those materials are diamagnetic. Because the spin moments cancel each other, and the orbital paramagnetism is quenched, is hindered, it doesn't really contribute to paramagnetism, and therefore the material becomes, or is actually, a diamagnetic. And that will happen in materials that have complete or filled electron bands. For example, materials like semiconductors, like insulators, like ionic crystals like salt, sodium chloride, they all have filled electron bands, and therefore they are all diamagnets. So, this is the whole idea between paramagnetism versus diamagnetism. Paramagnetism, the field is or enhances the magnetic moments that are created in the material. So they try to align with the magnetic field. In diamagnetism, they oppose the magnetic field. And that's why there's no net magnetic field. Is it clear, guys?
Yes, but I have one question. The paramagnetic material has a slightly ferromagnetic behavior because
A
the best
slightly paramagnetic behavior, is that? Sorry.
no the paramagnetic material has a slightly ferromagnetic
Ferromagnetic?
behavior.
So you're asking basically if a paramagnet is slightly a ferromagnet.
Yes.
Okay. Yes, we could say that there's a difference, and we'll see ferromagnetism in a bit. Bear with me. But yes, and there's actually a difference, right? In paramagnets, the thing is that all fields, or sorry, all spins will try to align with the field. In ferromagnets, there will be some spins that will not align, and so that will be the difference. But yes, you could say that paramagnets and ferromagnets are kind of similar. So yes, you could say that. I will actually say more than ferromagnets are paramagnets than paramagnets are ferromagnets. But yeah, there is a relationship between them.
Okay.
Now, what happens in materials that have partial field bands? Remember that because of the Hans rule, the electrons and spins in those materials with partial field bands are arranged in such a manner that the total spin is maximized, right? Why? Because, well, that condition is just energetically more favorable. For example, an atom with A valence d electrons, right? So basically, let's say a material that in its electronic configuration has D8. It's not that, and that is because of the Hans rule, it's not like you will have this. You will not have this. Okay, so that will be 4, 6, and 8, right? You have those 8 electrons. But again, because of Hans rule, he says, and oh, sorry, and yeah, because in D, remember, in D is filled with 10 electrons, right? D can hold up to 10 electrons. So let's say a D8 doesn't have this, right? Why? Because Hans rule tells me that the total spin moment must be maximized, right? So a material that has D8, for example, will actually have something like this. In those 5 levels, oops, sorry, we'll have 1, 2, 3, 4, 5, right? 6, 7, and 8, right? So that way it's maximized. And look what happens. 5 spins are actually aligned upwards, and 3 spins are aligned downwards. If you just look at this, then you have a total or net total of 2 spins up, because in this, okay, this one right here cancels cancel each other, they two cancel each other, they two cancel each other. Oh, but here I only have one spin up. And here I have another spin up. So I have two net spins going upwards. Well, then I have a net magnetic moment, and therefore I actually have two units of magnetism, and this will be paramagnetism, right? The smallest unit, the quantum unit of the magnetic moment is called the Bohr magnet. Okay? And the Bohr magneton, I just want you to know this constant is 9.274 times 10 to the negative 4 joules per Tesla, or that's equivalent to amperes per meter square. So basically, that atom that has D8 has two Bohr magnetons. So two of these. The Bohr magneton is the smallest or the quantum unit of the magnetic moment. So you could say, for example, that this material has two Bohr magnetons per atom. Because obviously this is per atom, right? Now, we should be very cautious on applying these principles because, as you might imagine, there are obviously exceptions. Yes, this applies for most materials, but not for all, because there are exceptions like copper. For example, copper has one s electron in its valence band, right? And because it has only one electron, right? So it will be S. S can hold up to 2, so that will be only one level, right? So it has one electron, so it will be just like that. So there is a net magnetic moment, just one, right? There will be only one unit of paramagnetism. So you will think, oh, then this material should be paramagnetic, right? But actually, copper is a perfect diamagnet. Well, not a perfect, sorry. I'm lying, it's not perfect. But it is a diamagnet. It actually has a diamagnetic behavior and not really a paramagnetic behavior. So there is an exception, and there is a whole quantum theory devoted to explain why there's that exception in copper, but we're not gonna focus on that. Other examples are superconductors. Superconductors will be the same, right? You will think, oh, there should be paramagnets because there is a net magnetic moment, but superconductors are also, and they are actually perfect, as I said when I was talking about diamagnetics, they are actually perfect. They are perfect diamagnetics when they are in the superconducting state, so when they are below the transition temperature. As I said, remember, right? They repel, so they're like a barrier for any magnetic flux lines. So it's just literally the superconductor becomes a wall, a very strong wall, that repels any magnetic flux lines that are incoming. And that's why it's a perfect diamagnet. Even though you will expect, if you were to draw the spins, there will be, depending on the superconductor, there will be one or two net magnetic moments left per atom, right? So Bohr magnetons per atom. But, and that is even a more complicated theory because that's related to the BCS theory, and that is related to the whole actual atomic structure of superconductors, and why is it that below the transition temperature they are perfect diamagnets. Above, they do, or the paramagnetic behavior actually becomes prevalent, but below the transition temperature, below the critical temperature, they are perfect diamagnets, and the paramagnetic behavior just doesn't exist or doesn't appear. Okay. Any questions so far, guys? No. Okay. Time for coffee break. Well, I don't see Georgina here. She was supposed to present the coffee break 2 weeks ago. But never mind. Okay, Nati, you were supposed to present it last week. Do you have your slides? Natalia? Natalia, are you there? Okay, apparently Natalia is not there. Okay, give me 1 second. Okay, was somebody else supposed to present today? I don't remember if I chose a person last week. Remove Natalia. Okay. Okay. Did I choose someone for this week?
I guess no.
Yeah, I probably forgot. Yeah, because I had 2 people remaining. Yeah, that's fine. Okay, so I'm gonna choose someone. I'm gonna choose someone for today. Let me go here. Go there. Okay, there we go. Okay, let's see. Becky, Becky, you haven't presented yet, have you? I cannot hear you, Becky. Becky, are you there? What happens with Becky Melina?
Hi, David. I'm sorry. My things just crashed for a little bit.
That's fine.
You
You
can.
have your slides ready?
Yes.
Okay, give me 1 sec. Becky, are you there? Has audio problems. Can you type, Becky, at least? If you have audio problems, can you type your response? Are you there? Okay. No. Okay, never mind. Bye, Becky.
Teacher,
Right.
Becky have problem with connections.
Okay, I see. Um. Okay, Nati, let's go, please. And can someone let Georgina know that she should be presenting today? Go ahead, Nati, please.
Okay. I'll share the screen.
Thank you. And does anyone remember if Becky presented already? I remember she did, but I think it was for herself and for this course. Go ahead.
She has not present, I think.
Thanks, Jose. Okay. So please let Becky know that she should present next week. Okay. Anyone, please just let her know. I think you guys have a group, so a group chat, so you can just message her and tell her that she should be presenting next week. Okay. Go ahead, Nati. Sorry for the interruption.
All right. So can you see the slides? Sorry.
Yes, we can. Yes.
Okay. So hi everybody. Today I'm gonna talk a little bit of conducting polymers. I mean a little bit of the application of them. Sorry, I'm having a trouble. I cannot change the slide. Sorry, just give me 1 second. Okay. So it's changing the slide. Sorry. I'm sorry, I cannot change the slide. I don't know what's happening.
Can you just send your slide, or do you have them in PDF format? You can send with PDF format if that's.
Yeah, I think I can share my screen.
Okay, so stop sharing and then try to share again, and let's see if that works. Stop sharing. What?
Can you see it? I'm sharing my screen.
Yeah, now I can see your screen too. Yeah.
Yes, it's a bit of a mix here. Okay, so yeah, as I was saying, I'm going to talk about conducting polymers. So we all know that electricity is basically the consistent electronic movement. Frequently, there are higher conductivity in metals, but some polymers can also conduct electricity because of their sorry, because of a very important feature about the conjugated structures they have in their main let's say structure. So basically a metal atom, let's say has higher orbitals, so they have free electrons since they're not really bounded to the nucleus, so they can actually have higher conductivities. For non-metal atoms, these orbitals are quite closer to the nucleus, and thus these electrons need further energy to conduct. So how do you conduct pi bonds are consistent dilocated electrons that are, let's say, they are kind of free, so they can easily move from let's say one station to another, as we can see here in the diagram. These not really bounded electrons move, and thus they can conduct. We have some examples. You can have polyethylene, polypyrrole, and polyaniline. Also, some polyacetylenes can conduct electricity. They were one of the first ones to be discovered. Also, to enhance these properties, we can add some additives for adding or removing, as we know, an N-doping or P-doping, in order to generate more current carriers, maybe as holes or electrons, or free electrons. So some of the examples in which we can use these conducting polymers are, for example, in this example, for example, in this research, where they used polypyrrole grafted gelatin-based hydrogel to conduct, which is a conducting gel that heals itself when a current is applied. Here's some of the polymer used in this research, and in this study they added, or they grafted polypropylene. And what about day-to-day life? In our daily life, we can use, let's say, for illumination, incandescent light bulbs, which actually work with a wire filament. And when a power is applied, this resistance can cause a lot of heat, and thus this wire glows. Now, with LEDs, which is light-emitting diodes, this generates a light, or let's say there's some stimulus with the power, so it's like a little discharge, which we can see as light. Yeah, one of the benefits of LEDs, as we know, it's that they don't really get hot, and it's a little bit more power efficient, energy efficient. Now, I know that you have heard about OLED, which is an organic light-emitting diode. These OLEDs that we have in our computers and in our computers screen are made out of these polymers, these conducting polymers. And here we have a little schematic of the cell they use. So we have a cathode, we have an emissive layer, the conductive layer, which is going to be the polymer, and the anode. So basically what happens is that when our power is applied, the electrons from the anode go to the cathode, and this change of electrons, while they pass through the emissive layer, they create this, well, they don't create it, but they generate these energy pulses. That's why these LEDs and OLEDs, they have a frequency in which when you record them, they are like turning on and off, because it depends on the frequency that these electrons move from, or how fast they move from the anode to the cathode through the emissive layer. Well, some of the advantages of the OLEDs are that they are 10 times thinner than regular LCDs, which was like a very regular form of the screen like 10 years ago, I think. Also, they are flexible. Usually for LCDs, to create a black color, we just turn off that LCD pixel, let's say. But with OLED, they create black. So colors are way better. Also, OLEDs are faster. This electronic movement from the anode to the cathode, it's way more faster than with LEDs, and with in comparison also to LCDs. As I was saying, they generate true blacks and true colors. And some of the disadvantages of this is these polymers, since they're polymers, sometimes they can degrade in certain situations, like maybe too hot environments, or when they are surrounded by water. Well, other application of conductive polymers, it's tissue engineering, fuel cells, some of these engineering gels as well, for rehealing itself, also as a scaffold for, as I was saying, for tissue engineering. And well, they do generate a more efficient, energy efficient products, and thus they are polymers. So this is quite cheaper to do in comparison to metal, and energetically talking as well. They can be way more energetically efficient in their production. That's it. Thank you.
Great. Thanks, Nati. Does anyone have any questions for Nati? I have a couple of questions, Natalia. Why would you want to use a conductive polymer in tissue engineering?
Why? So as we saw in the slide, they can be heal itself. So let's say you have, I don't know, maybe kind of cartilage. I was reading about cartilage. They use them in your arms basically. So they use these conducting gels in junctions. I don't know how joints in your joints. So as I read, this also will help with the what is it?
But I don't get how does the conducting effect help on this? Because and I know they're useful. I just want you to answer that. Why are they useful? What's the conductive? What does the conductive effect do on these polymers? Because they are just self-healing polymers. They don't need that conductivity to heal themselves. Why do you need to put something conducting that can conduct electricity in your body? That's my question.
Well, that's a hard question, and I know that I read it actually. Um, I know that I read it. It's a very harsh question. Just let me think. Okay, so I might need a kind of, I don't know, maybe for nerves,
That's fine. That's fine. Go ahead.
maybe for nerves in joints. I read about this conducting gels, but not really. Yeah, not really for tissue engineering. These polymers, as I read, they can be they have very good bioadhesion.
They have what?
So bioadhesion, so your body will not like pulse it. Um, I read about heart tissues and some of like joint tissue, but yeah, to be honest, I don't quite remember why they use especially the conducting, the conducting feature for
That's
joints.
fine. Okay. Go and research on that. That's and not this doesn't go only to you. Go and research that, guys. It's interesting. Why? Because to me it sounds crazy. Why would you use a conducting polymer in your body? And it doesn't have to do with the fact you were saying or you were mentioning self-healing polymers, right? And yes, that's nice because yeah, they can self-heal and hopefully help to heal a joint or something. That's fine. But why does it have to be conductive? That's the big question. Why do you want to put actually something conductive in your body? Why is that a requisite to and why is it that some polymers need to be conductive when you go and put it in your body? That's something you guys should research, and you should know it. It's very interesting. Okay, so I'm gonna leave that question for all of you, not only for Nati. And I guess my takeaway message here for everyone, and I say this not only to you but to all my other courses too. Whenever you're and this is, trust me, this is a very good advice. For your next semester that you guys will be doing your materia integradora, when you're talking about something or when you mention something, make sure you know what you're, even if you just look at what Nati did. Nati was explaining a lot about, or I guess to me at least, the main application you mentioned and the one you mostly focus on was the organic LEDs. right? And how conducting polymers are using organic LEDs, and how are they better than the normal LEDs that you have. But you mentioned at the beginning that you were going to talk about different applications of conducting polymers. And then towards the end, you mentioned that one of the applications is tissue engineering. So you just mentioned that, but you didn't explain why is it important to use conducting polymer in tissue engineering. And again, this is nothing against you, and this is actually take it as an advice, especially when you guys start your materia integradora. I'm not sure if I'm gonna be one of your evaluators, but whenever you mention something, make sure you know that. Okay. Because otherwise, you know, some professors will pick on that and start asking on that. And it actually happened to me on my master's degree. I briefly mentioned something. It was not, probably it wasn't even the most relevant thing, but then one of my evaluators started picking on that. And he literally didn't want to move on until I answered that. So make sure if you are going to mention something, make sure you know it. Okay. Because otherwise you might fail your viva. Viva is your defense of your project, right? So that's just more an advice to everyone. What did Miguel say? I guess you try to explain that it is how osteogenesis happens in muscle cells grow when it is present in nerves. Yeah, but that's not the answer. Yes, she was trying to explain how how it might be related to nerves. But it doesn't really have to do like if you put like a gel there, like in a joint. It doesn't really have, or it doesn't have like a close connection to nerves. And I mean, it was nice. Nati was trying to answer. Go ahead, Nati.
Oh yeah. Isn't it because of the of the uh, of the growth of the cells? Like they do they need this kind of electrical conductivity to in order to actually grow and exchange whatever they change with other cells or something like that?
Yeah, go and research that. It's interesting. It is related, yes. But go and research that.
Okay, check.
That's gonna be your homework for all of you. Bioactivity is important in tissue engineering, yeah, but how does bioactivity is related to conductivity, Jose? That's the question to answer, right? Because again, Natalia was talking about conducting polymers. Why do you need a conductive polymer? It's very interesting. So go research on that. It's quite interesting. Okay, actually, that's gonna be one of. Oh, by the way, on Wednesday, you guys will have an assignment. It's ready. So I'm gonna add this question, so you guys, all of you, go and look into that. I'm gonna add that question to the assignment. But it's a very interesting topic. Okay, so again, go and whenever you, just my takeaway message, no, if you know, if you're gonna mention something, make sure you know that. And because it's fine not to know something, that's fine. Like, and especially like all of us don't know a lot of things. Even I don't know a lot of things, right? And especially about polymers. If you start talking to me about a lot of polymers, I just know the basics of polymers. I know some applications, but that, like, I'm not an expert in polymers at all. But so whenever you're talking about something, make sure you know about that, right? Just again, that's more of advice. It's not really about your presentation. Your presentation was nice. It's an interesting topic. I like the fact that you mentioned about disadvantages, not only the advantages or the nice things. I like the fact that you also mentioned disadvantages, even though you could have focused or you could have mentioned a lot more disadvantages. Because yes, it's nice, it's more energetically efficient to produce. It's actually more energetically favorable in terms of like saving power and energy, yes. But there are a lot of other disadvantages, not only that, let's say a metal it's a lot more involved or more it requires a lot more energy to produce a metal, but also remember that polymers they have a lot of other compounds, and especially for example in OLEDs, in those organic LEDs, you have a lot of other toxic materials, and it cannot be just thrown away, right? So you could have also mentioned more disadvantages of these materials, but again, in general, I really like the presentation. This was just more of an advice for everyone, especially for you, again, for your upcoming semester. Make sure that when you mention something, make sure you know something, guys. There's nothing against you, Natalia, and nothing against anyone. This is just a general advice for your life and everything, right? When you're talking or you mention something, make sure you know that. Because you might have questions on that, and then you don't. If you obviously don't know how to answer, or you don't know the answer, sorry, then people will be questioning, right? Why are you talking about that if you don't know that? And then obviously it's fine to not know something. Yeah, I think you guys have asked me a couple of questions that I haven't known the answer. And what I told you is I don't know the answer. I'll look into it, right? I think that happens once in metals, and I don't remember if it happens in this course. And it's fine not to know something, for sure. Like, no one knows everything. That's fine. And then obviously, if you don't know something, just say, okay, I don't know. I'll probably go and look for the answer, and that's fine too. Okay. But especially for your projects, for your materia integradora, just be very careful when you mention something or argue something. Make sure you really know how to support that. Okay, that was just an advice, guys. Nothing more than that. Okay, let's go back to the slides. Any questions, by the way? Okay. Becky, are you there now? Can you hear us?
Yes, mister. I'm
Okay.
here.
You'll be presenting next week, okay?
Yes. Okay.
Cool. Okay, let's go. Let's continue. Okay. So, enough for para and diamagnetism. We'll come back to them in the next week once we start relating this to quantum behavior, but we'll come back to that. Okay, let's go to ferromagnetism. Let's imagine you have a newly cast piece of iron and you put it into a solenoid, obviously a ring-shaped solenoid. As you know, that solenoid has a magnetic field within the coil, within the turns, right? So if the external field strength is increased, once I increase obviously the current, remember that the field strength is directly proportional to the current, if you remember the equations in the first slides. If I increase the current in the winding in the coil, obviously the external field strength will be increased. Well, then what's going to happen with the magnetization? It will also rise. But it will actually rise slowly, right? It will first rise slowly, like this part. It rises slowly, and then it rises rapidly until it levels off. And it reaches a saturation value that's called the saturation magnetization, that's MS. Okay? Now, if I remove the magnetic field, so my magnetic field strength becomes 0, what happens? I have a remanent magnetization. So it doesn't go back to 0, right? It comes back to a remanent magnetization. So that's MR. And it's actually this remanent magnetization, the one that is used in permanent magnets. If you guys remember from your ceramics course, we saw 2 types of magnets, permanent and non-permanent magnets, or as we call it, soft and hard magnets. Well, this remanent magnetization is the one using hard magnets, right? And permanent magnets. So that's why they are called permanent magnets, right? Because they have this remanent magnetization. Now, can I remove that magnetization, that remanent magnetization? Yes, for sure. If I reverse the magnetic field strength. So if I reverse my magnetic field, right, I basically change the direction of that magnetic, then I will get a coercive, or up to I get the value of the coercive field, that's Hc. Once I get to that coercive field, then yes, my magnetization becomes 0. Okay, and then I can keep like doing that. That means reversing completely the field, for example, and then again going back, and I can actually form a loop, a hysteresis loop of magnetization. And that's why, if you remember, I think we saw this, all those materials that have a large combination of the remanent magnetization and of the coercive field, so all those materials that have a big area of this hysteresis loop, they are all hard magnetic materials, because it's very difficult for those materials, almost impossible, sorry, to get it back to 0 magnetization, right? That's why they're called permanent magnets, because they have a huge area within this curve. Whereas those soft magnets, if you remember, they have a hysteresis loop like this, right? They have a very tall, but something like that, right? You know, I'm terrible at drawing, but they have something like that. So it's a tall loop, but it's not white. So it's a tall loop, but it's not white. So it's very easy for them to come back from this remanent magnetization to this coercive field value, right? Very easy. So that's what they're called soft magnets, right? Whereas in permanent magnets, I remember this, right? It's a huge, right? I'm terrible at drawing, you guys know that, but something like that. So it's a big area. So it have a large value of remanent magnetization and coercive field. That's why it's so hard for them to go back to 0 magnetization, and therefore they're hard or permanent magnets. So this is the most popular curve, magnetization versus magnetic field strength. Now I can have another type of hysteresis curve, in which instead of using the magnetization, we use the magnetic flux density. But that would be the same. I mean, it's the same principle. Obviously, in that case, there will not be a saturation value, because the magnetic flux density doesn't have a saturation value as the magnetization does. But in general, it's the same principle. And as I said, this is the most popular curve, the magnetization versus magnetic field strength. Okay. Any questions? Oops, sorry. Okay. Is it clear, guys? Any questions? Let's go. Now, the saturation magnetization, as again I repeat, most constants, is temperature dependent. As I said, remember, only in diamagnets is that the constants are not temperature dependent. In all other type of magnets, the constants are temperature dependent, and obviously the saturation magnetization is not the exception. So above the Curie temperature, the ferromagnets become paramagnets. And this, I guess, was the question of Jose. So above the Curie, that ferromagnetic behavior becomes paramagnetic. Okay, here you can see the Curie temperature for a few metals. And in ferromagnets, the Curie temperature and the constant theta, remember I said is also a temperature constant. In the Curie-Weiss law, remember that law? Curie, where susceptibility equals Curie constant divided by temperature minus the constant. They're nearly identical, right? The Curie temperature and theta are nearly identical. There will be a small difference, right? Because of the transition from ferromagnetism to paramagnetism, but then it's basically the same. So you can see here, below Tc, below the Curie temperature, the material is ferromagnetic. Above the Curie temperature, the material is paramagnetic. Now you might be wondering what MS naught is, that you can also see it here, what MS naught is. What MS naught is just the magnetization, or the saturation magnetization at 0 Kelvin, that's why it's not, okay? It's the saturation magnetization at 0 Kelvin, and it's giving in amperes per meter, and you can see the values there too, okay? So you can see that the saturation magnetization with temperature, you can see what happens when it's a ferromagnet. It decreases, right? And once it becomes paramagnetic, then it increases. And actually, you can already start seeing this. There's a relationship of 1 over chi. That's for paramagnets. 1 over chi, right? That is once the material becomes paramagnetic. The saturation magnetization is inversely proportional to the susceptibility. Okay? Now, within ferromagnetism, within this behavior, I actually have the piezo-magnetism behavior. So these ferromagnetic materials will usually have unfilled D bands. Okay? Or in general, they will have unfilled bands, not only D bands. They will have unfilled electron bands. So the spins of those unfilled bands will spontaneously align parallel to each other below the Curie temperature. So when the material is ferromagnetic, right? So remember, I did mention that domains or magnetic domains are created inside the material, right? So those domains will basically start being magnetized until saturation is reached. The spin direction in each domain is different. so that the individual magnetic moments for the material as a whole cancel each other, and we have a net magnetization of 0. Now, if I put an external magnetic field, what will happen is that those domains whose spins are parallel or nearly parallel to the external field will start growing at the expense of the unfavorably aligned domains. So basically, it's this. You will have this, right? Look at this, for example. That is the direction of the field, right? And compare this versus this. So you can see that the one in the middle, right, that is more favorably oriented, or it's actually oriented with the field, it starts growing or expanding, and the others that are not aligned with the field, they become smaller. The ones that are aligned with the magnetic field, they will start growing at the expense of the unfavorably oriented fields. Okay. Until eventually I have my entire crystal, my entire material containing only one single domain, where all spins have a line parallel to the external field direction. When that happens, the material is said to reach the technical saturation magnetization. Right? So just the MS is just the saturation magnetization is the same. Now, what happens if the external magnetic field is further increased? Obviously, there will be a slight increase in M as well, so a slight increase in the magnetization. And that will just be due to the alignment of those spins that were already aligned with the field, right? The largest magnetization that the material can get is the MS0, so the magnetization at 0 Kelvin. If I increase the temperature progressively will destroy that spontaneous alignment, and eventually I will have a transition to paramagnetism. Any questions so far? So the largest magnetization a material can get is when it's basically at 0 Kelvin, and that's the MS0 value that we saw in the table here. Okay. Oops, I think I missed this slide. Sorry about that. I'm gonna come back to this slide. Okay. So it's the one here. That's MS0. And as I increase the temperature, that alignment that I have, so this alignment, let's say, right, that I have, it will start to be destroyed. And obviously, the more I increase the temperature, I probably reach the Curie temperature. And if I reach the Curie temperature or go above that, obviously that alignment that I see here, will be destroyed, and the material will become paramagnetic and not ferromagnetic anymore. Okay. I forgot, as I said, to go through this slide. I'm sorry. The magnetization of ferromagnetics is also stress dependent, and that's why It's actually this phenomenon. This is related to piezomagnetism. But piezomagnetism, again, is just a subset, I will say, of ferromagnetism. Okay? So the magnetization of ferromagnets is stress dependent. For example, if I put a compressive stress on a material, that will increase the magnetization, and that happens, for example, in nickel. Whereas if I put a tensile stress, it will actually reduce the magnetization. And if the magnetization is reduced, also, how was this called, guys? How was mu called? Permeability, okay?
Permeability.
Yeah, so if I apply a tensile stress, I will reduce the magnetization and the permeability. Whereas if I if I put a compressive stress, I will increase the magnetization and I will also therefore increase the permeability. That happens, for example, in nickel. So there are some ferromagnets like nickel that show this magnetization dependency on stress. Whereas if I put, for example, a nickel iron alloy, it's the opposite. A tensile stress will increase the magnetization and therefore the permeability. And if I put obviously a compressive, it will decrease, right? And then, so I do have certain materials, iron too, and iron actually is a bit more complex. Iron, if I'm at low fields, the iron behaves like a permalloy. Permalloy is a nickel iron alloy, okay? Whereas if I put a high field, it actually behaves like similar to nickel. Right? So that is called piezomagnetism. It's just because the magnetization of the material depends on stress, if it's a compressive or a tensile stress. And as I said, it really varies from material to material. There's not a single law, okay? You can see here for nickel, if I put a tensile stress, the magnetization increases, right? If I put no stress and if I put compressive stress, look, so when I have no stress, okay, so I have a value, right? With compressive stress, what happens? I increase the magnetization. With tensile stress, I reduce the magnetization. Whereas in iron, look, it's the opposite, as we said, right? So no stress is here, the solid line. Compressive stress, look, it actually reduces the magnetization, and tensile stress, it increases it, right? So you can see the different behavior between nickel and iron. But look at this, the stress does have an effect on the magnetization. Okay? So if you have, I don't know if you guys have fluorescent lights in your home. If you guys have fluorescent lights, I don't know if you've heard that humming noise, right? Of like when you turn your light on, if you have a fluorescent light, a fluorescent bulb, it kind of makes a sound, right? Like a right? And it kind of makes a sound like that, or like zzz, I don't know. I'm terrible also at doing sounds, but like if you have fluorescent light and you turn it on and you get close to your bulb, it will hear something like a small noise, like well, that noise actually is related to piezomagnetism, right? It's actually related to that change caused by the alternating magnetic field, okay? And so in the stresses that are generated in the magnetization being changed. Okay. I can have the opposite effect also in ferromagnets. And actually it's also observed in ferromagnets and in antiferromagnets. It's this magnetostriction effect. That's just a change in dimensions when I expose the material to a magnetic field. Yeah, so this. Now you might be wondering a couple of questions, or at least there are a couple of questions to be answered with these explanations, right? For example, why is it that in the spontaneous division into many individual domains prefer to one single domain? So why is it that instead of having only one single domain, I actually have a division of many domains? And then yes, again, as I said, the domains that are favorably oriented, they will start consuming the other ones, yes. But why is it preferred to break into many domains rather than have only one single domain? Well, let's just assume that all electron spins in a crystal are all indeed aligned in parallel to the external electric field. If I will have that, I will actually have a dipole created, right? Because all of the spins are aligned parallel to each other. Well, that will be very unfavorable in terms of energy, because that will generate a large external magnetic field, and that will produce a magnetic field. Well, the energy of that field, the magnetostatic energy of that field, can be reduced and actually can be cut to half if the crystal contains two domains that are magnetizing opposite directions. And then if I keep dividing or breaking into smaller and smaller domain, well, that will reduce the magnetostatic energy until I get an optimal domain size and an optimum value of magnetostatic energy. Right? So it's just because it will be very unfavorable in terms of energy to have only one single domain, because a dipole will be created because all of the spins will be aligned parallel to each other. Now, there should obviously be an opposing mechanism. As we know, every force has a reaction, right? Every action has a reaction. So there should be an opposing mechanism, and yes, there is. The energy that is involved for this opposing mechanism is called the quantum mechanical exchange energy. That energy sort of leads to the fact that some adjacent spins will align parallel to each other. So I have the magnetostatic energy saying, oh no, it's unfavorable, please don't align with each other. And I have the quantum mechanical energy saying, you guys have to do it. And so that interplay between magnetostatic energy supporting anti-parallel spins and the quantum mechanical exchange energy demanding parallel spins leads to an energetically most favorable domain size that's usually between 1 and 200 micrometers, and that's why you see this. A lot of domains, obviously, one's a lot bigger, or some a lot bigger than the others, and those bigger are the ones that are favorably oriented to the magnetic field. Now, you might be also wondering, is the flip from one direction to the other sudden? Like, does that happen, that reversing of the field that I've been talking about, does it happen at once, like super fast? Does it happen between two adjacent atoms, or does it happen like over an extended range of atoms? Well, this exchange energy that again, supporting parallel spin hinders or prohibits or blocks a spontaneous flip over. So it doesn't happen from atom to atom. It's not that, okay, one atom, right, is aligned, let's say, on the positive or upwards, and then the adjacent atom will align, or in the adjacent atom it will be aligned downwards. That doesn't happen. Actually, that rotation or that flip from one direction to the other happens gradually over 100 atomic distances. And because obviously it's more energetically favorable, right? You will consume less energy rotating slightly until you end up in the other direction, rather than changing suddenly from one direction to the other. Those domains, or sorry, that region between domains in which the spin is rotating from one direction to the next is called the block wall. Remember? Okay. So that basically this here, this line here, that is called the block wall, because it's literally a wall in which the domain will eventually start rotating and will eventually at some point flip over completely to the opposite direction. Okay? Any questions, guys? Okay. That'll be it for today. I'll see you on Wednesday, guys. Take care and have a good day.
Thank you,